Welcome back to the deep dive. If you've been following the world of computing, you probably know we're kind of in the middle of this unprecedented computational crisis.
Yeah, that's putting it mildly.
We're just demanding more speed, more complexity, more AI capability than, well, our current hardware can sustainably provide.
Hmm.
This is where we hit that, the digital wall, the hard limit of what electrons can actually do.
That wall is absolutely real, and the energy bill that comes with trying to punch through it, it's astronomical.
Right.
For years, we've heard the refrain that Moore's law, the traditional doubling of transistor density, it's slowing down.
Definitely slowing.
And now we're seeing the complexity of deep learning tasks, things like large language models, really push our existing hardware architectures to the absolute breaking point.
So, okay, if electrons can't take us further, what's the answer? It feels like we need something radically different.
Well, the paper we're looking at today proposes a literal shift in medium.
Ditching electrons for photons, using light to compute.
Exactly. Light.
Today, we're undertaking a deep dive into a really revolutionary paper, an integrated, large-scale photonic accelerator with ultra-low latency.
Quite a title.
It is. We're going to unpack the architecture of this thing called the Photonic Arithmetic Computing Engine, or PACE,
Okay.
and try to understand how it delivers computational cycles measured in single nanoseconds. That's billionths of a second.
And here's the headline that should really hook you, listener.
Yeah.
For certain computationally hard problems, this light-based accelerator, PACE-E, has been benchmarked as nearly 500 times faster per cycle
Whoa.
than a high-end commercial GPU.
500 times
Right.
per cycle. That's staggering. Okay, let's unpack this. We need to understand the full mechanics here.
Right.
Our mission today is to understand why light grants such ultra-low latency, how the engineers actually managed to scale optical components from, a lab curiosity into a functioning integrated chip.
Which is a huge leap in itself.
Huge. And what this leap means for the future of solving complex, real-time optimization problems. Problems that are currently just too slow to solve practically. All right, so to really appreciate the solution, PACE-E, we first have to understand the depth of this crisis, the digital wall. If you had to point to the single, most power-hungry, latency-inducing task at the heart of nearly all modern AI and deep learning, what is it?
Oh, it all comes down to the matrix multiply accumulate operation, usually shortened to MT.
MSC.
Think of the MAC as the computational heartbeat of any neural network. Seriously.
Your core engine?
Absolutely.
Okay.
Whether you're training an AI or just using it for inference like asking ChatGPT a question, the system is performing billions, maybe trillions of these MBASI operations.
Trillions. Wow.
They're absolutely pivotal. They form the mathematical core of machine learning, and they consume the vast majority of resources, both computational cycles and power.
So when we ask an AI to handle a larger, more complex matrix-like, say, trying to recognize a really high-resolution image or predict a super complex financial model, we're basically just drastically increasing the volume of these MACE operations.
You got it. And that's precisely where the electron-based systems start to really strain.
That's the bottleneck.
That's exactly where the bottleneck lies. If you look at state-of-the-art digital systems, your GPUs or specialized tensor processing units, TPUs, they rely on a digital approach, often built around something called systolic arrays.
Systolic arrays. Okay, that sounds fast and complex, like a perfectly coordinated dance.
Yeah, that's a decent analogy.
But what does that term mean in practice, and why does that architecture apparently fail at the highest scales?
Well, it is a parallel processing system, but crucially, it operates digitally.
Meaning?
Meaning the movement of data is fundamentally sequential, even if it happens very, very quickly. The digital logic inherently decouples these essential dot product operations that make up the MAC. And think of it like a massive city traffic network. Each piece of data, the weights, the inputs, it needs to move from one processing unit to the next, like cars moving through intersections one after the other.
Ah, okay. So instead of everything happening simultaneously in one spot, you've got data constantly traveling, maybe stopping, getting processed, then getting transmitted again to the next spot.
Precisely. And that results in substantial data movement between neighboring units right there on the chip architecture.
Okay.
And every time you move that data, you hit two major obstacles. First, it requires multiple clock cycles to complete a single large matrix operation. It's not instantaneous.
Right, takes time.
Second, and this is the killer, really, every time an electron moves through a wire, you encounter resistance. It's physics.
And resistance means?
Heat. That resistance generates heat, We call it resistive loss.
That's why these massive server farms need equally massive cooling systems, right? They're literally fighting the physics of the electron.
Correct. They're fighting thermodynamics. And the source material, the paper, shows compelling evidence here. In traditional digital systems, as the matrix size expands, as the problem gets bigger, the accumulation of all that data movement and the multi-cycle computation causes latency to grow substantially,
Not just linearly, but substantially.
often by orders of magnitude. So the bigger the problem, the disproportionately slower the solution becomes.
That sounds like a recipe for hitting a wall.
It is. This, let's call it exponential scaling of latency, it exacerbates both power consumption and the heating issues that electronics constantly battle. We are quite literally hitting a thermal and power limit imposed by the movement of charged particles by electrons.
Okay, so we've got this fundamental problem. The core task of modern AI, the MA operation, is limited by data movement, resistance, heat, and this substantially increasing latency. Feels like an unsustainable trend.
It really is.
So if we can't make electrons move much more efficiently, the shift to something fundamentally different seems, well, almost inevitable. We have to move to photons.
And this brings us to the optical promise. Now, it's important to note, optical computing isn't some brand new idea that just appeared.
Right, I've heard about it for years, decades maybe.
Exactly. Scientists have explored it for decades. But the breakthroughs needed to move it from a cool concept to a scalable reality. Things like innovations in silicon photonics, nanophotonics, advanced materials, science, they've only really arrived relatively recently.
And that's driving this massive resurgence of interest we're seeing now.
That's right.
Okay, let's get granular on the physics then. What is the fundamental physical advantage of light? How does a photon perform a Macastart operation more efficiently than an electron? Because that seems like the magic trick here.
The advantage is inherent in the wave nature of light itself. Unlike electrons, which carry a charge and have to physically travel down a wire, path by path,
Right.
light signals can be superimposed. They can occupy the same space at the same time.
Yeah.
Photonic computation relies on what are called guided wave circuits. Think of them like tiny optical fibers etched onto a chip. Light beams containing the input data and the weights are directed to interfere with one another within these guides.
Wait, interference, like noise-canceling headphones use interference. Or ripples in a pond meeting.
Exactly like ripples in a pond. That's a great analogy.
Huh.
When two light waves meet, their amplitudes combine, constructively or destructively.
Okay.
In optical computing, that combination, that interference pattern, directly performs the multiplication and accumulation of signals, the MAC operation, simultaneously.
Hold on. The math happens as the light travels.
Yes, the entire mathematical function is completed in transit as the light propagates through the circuit.
Wow. Okay, that's a profound shift in thinking. The calculation isn't performed by sequential steps in a logic gate.
No.
The calculation is the propagation of the physical wave itself.
That's right. And this leads to massive parallelism. It drastically reduces the need for data movement because the core math is handled optically all at once.
And less data movement means less energy.
Exactly. You conserve energy because you avoid the resistive losses of electrons moving through wires. And you entirely sidestep the complex digital communication overhead, the traffic jams that plague electronic chips.
Okay, so if digital latency grows, as you said, substantially, meaning rapidly, maybe exponentially with matrix size, how does light handle scaling? This seems like the critical architectural advantage.
Latency is the key metric here, absolutely. In photonic circuits, or OMA, as the paper calls it, optical MAC.
OAC, got it.
The latency is limited only by the physical length of the optical path the light travels.
Just the speed of light in silicon, basically.
Essentially, yes. And crucially, this latency scales linearly with the size of the matrix.
Linearly. Okay, what does that mean practically?
It means if you double the size of the matrix, the latency increases, sure, but only by a tiny proportional amount. It's just related to the slightly longer physical distance the light has to travel on the chip.
Give me the starkest contrast from the source material from the paper to really illustrate this difference.
Okay, the paper explicitly compares the growth factor. While electronic systems, like TPUs, see latency accumulating by orders of magnitude as matrices expand.
Right, that substantial growth.
The growth factor of optical M/C latency is measured in just several picoseconds.
Pico! That's a trillionth of a second.
A trillionth, yeah. This growth factor is nearly 1,000th of the growth seen in TPUs for the same increase in matrix size.
1,000th. Okay, that's negligible growth, practically speaking.
For practical purposes, yeah. Even for very large matrix sizes, the optical latency remains limited to just nanoseconds. It's tiny compared to the thousands of nanoseconds required by traditional digital circuits for large matrix MANCs.
That structural reality linear scaling versus substantial scaling, that feels like the foundation of why this is potentially such a significant breakthrough.
It is.
But as you mentioned, the dream of optical computing has, historically been constrained by engineering. Making one small optical component is one thing. Making an entire integrated, scalable system that works reliably, that sounds like a whole different ballgame.
That was the massive hurdle for decades. Past demonstrations were often limited to proofs of concept, maybe a single component or a very small circuit.
Right.
The real challenge, the one addressed by this paper, and the reason it's so important, is the demonstration of very large-scale integration and proof of volume manufacturing compatibility.
So actually building it big and building it reliably?
Yes, they had to successfully integrate thousands and thousands of these delicate optical components and make them all work together consistently on a single chip. That's the engineering triumph here.
And that leads us directly to the hardware solution they built. PACE, the Photonic Arithmetic Computing Engine.
Right.
What are just the sheer statistics of this chip? How big is it? And how did they manage that integration challenge we just talked about?
Okay, so PACE is designed as a high-density 64 by 64 matrix vector computing acceleration chip.
64 by 64. Okay, that's a decent size for these kinds of problems.
It is. And the sheer magnitude of the engineering effort is clear when you look at the component count. It integrates more than 16,000 individual photonic components.
16,000 on one chip.
16,000. Things like optical modulators, photodetectors, waveguides, splitters, combiners, all crammed onto a single piece of silicon.
Wow. How do they manufacture that?
They used a commercial 65-nanometer silicon photonics technology process.
Ah, so something that already exists in foundries.
Exactly. That's key. It means the fabrication is potentially compatible with existing semiconductor industry infrastructure, which is crucial for eventual commercialization.
16,000 components.
Yeah.
That's incredible density. But let's tackle the complexity. If light is so efficient for the calculation, why do they still need electronics on this chip? Doesn't including electronics immediately introduce some of the very latency problems they're trying to solve?
That's a really perceptive question, and it speaks to the fundamental limits right now of purely optical technology. Pure optical circuits, as they exist today, inherently lack efficient storage. There's no simple, non-volatile way to just hold a state or store memory purely in the optical domain, like you can with electronic transistors.
Ah, so light is great for calculating on the fly, but not for remembering things.
Pretty much, yeah. Therefore, photonic computing, at least for now, must rely on optical-electronic cointegration. They have to work together.
A hybrid system.
A hybrid system. And the researchers developed a brilliant hybrid architecture to do this.
Okay, so how did they physically merge light and electrons without creating new, inefficient bottlenecks? That sounds tricky.
They employed an innovative packaging approach. It's called 2.5D hybrid advanced packaging, specifically using a technique called flip-chip bonding.
Flip chip. Okay, what does that look like?
Imagine two distinct chips, two separate pieces of silicon, one designed for the light stuff, the photonics, and one for the electron stuff, the electronics.
Okay.
And they're stacked almost seamlessly together, face-to-face, connected by tiny electrical bumps, all within a single system-in-package, or SiP.
So two specialized chips working as one unit.
Exactly. You have the photonic integrated circuit, the PIC.
PIC for photonics?
Right. And the electronic integrated circuit, the EIC.
PIC for electronics. Got it. Let's break down the roles then. What exactly is the PIC, the optical part, responsible for doing?
The PIC is purely the calculation engine. It's dedicated solely to that high-speed 64 by 64 optical AMC operation we talked about.
Oh.
External laser light gets coupled into the chip. It flows through an array of modulators which encode the input vector data onto the light.
Turning electrical signals into light patterns.
Yes. And then that modulated light passes through this massive grid, the weight module, which is essentially a complex network of waveguides where the light interferes.
And that interference performs the computation.
That interference is the computation. So the PIC is essentially a passive but highly precise optical calculator.
Passive meaning it doesn't need much power itself, just the input light.
Largely, yes. The main power draw is the external laser providing the light source.
Okay, and the EIC, the electronic chip, built on, what, Standard CMOS technology.
Yeah, commercial 28 nanometer CMOS technology. The EIC acts as the support staff, the controller, and the translator between the two domains.
The brains of the operation.
You could say that. It houses the embedded static random access memory, the SRAM.
For storing the data and weights.
Exactly. It stores the input data, the matrix weights. It also handles all the logic and control signals for the whole system. And crucially, it manages the high-speed conversion necessary to bridge the optical and electronic domains.
Ah, the translation step.
Right. This includes the electrical to optical, or EO conversion, using drivers to control those modulators on the PIC.
Turning electronic bits into light signals.
Yeah. And then, at the receiving end, after the light has done its calculation on the PIC, it needs to manage the optical to electrical, or OE conversion.
Turning the resulting light pattern back into electronic signals.
Precisely. Using an array of photodetectors and high-speed transimpedance amplifiers, or TIAs, on the EIC to convert that faint optical signal back into a usable electronic voltage or current.
Okay, listening to that, it sounds like the overall system speed might be limited not just by the light path on the PIC, but maybe more by the efficiency and speed of those conversion steps. The modulators, the photodetectors, the TIAs, the ADCS sticks probably involved.
You've absolutely identified a key point and potentially a future limitation. We'll definitely circle back to that.
Okay.
But for now, the successful integration of these 16,000 photonic components with the control electronics in this 2.5D architecture is the core breakthrough that enables this large-scale application in the first place.
Right, just getting it to work at this scale is huge. Now, we have to address what you call the analog hurdle. Since light performs computation via physical interference, it's operating in the analog domain, not digital ones and zeros.
Correct. It's continuous values.
And analog signals are notoriously vulnerable to noise, to drift, to temperature changes, all sorts of imperfections. When you scale that up to 16,000 components working together, how on earth did they prevent all that potential noise from just killing the computation accuracy?
Yeah, this was perhaps the most rigorous part of the engineering challenge described in the paper. Maintaining high accuracy across such a large-scale analog system is immensely difficult.
I bet.
Their mitigation strategy was essentially meticulous manufacturing control, extreme precision. They designed all 16,000 integrated components with extremely tight specification variation.
Meaning they had to make them almost perfectly identical.
As close to functionally identical as possible within minuscule tolerances. Things like the path lengths in the waveguides, the efficiency of the modulators, the responsiveness of the detectors.
Why does that tight control matter so much for the light calculation?
Because in analog systems, any inconsistency, any variation between parallel paths or components introduces errors and noise. It ruins the signal-to-noise ratio, the SNR. If one light path is slightly longer or has a slightly different refractive index than the path next to it, the resulting superposition, the interference calculation, will be corrupted. The answer will be wrong.
So by ensuring all the components are incredibly consistent, they minimize those physical variations that would otherwise lead to noise accumulating across the chip.
Exactly. They're reducing the sources of analog error at the most fundamental level.
And what was the measure of their success in beating this analog hurdle? Did they quantify the improvement?
They did. The paper reports that the PACE design achieved more than 12 dBs of SNR improvement compared to commonly reported photonic designs or earlier smaller scale attempts.
12 decibels. That sounds significant in signal processing terms.
It's huge. That 12 dB difference is basically the margin that makes large-scale analog computation viable. It means the signal carrying the actual result is far, far cleaner and more dominant than the background noise generated by the system itself and its imperfections.
Okay, we've established the problem, this digital wall. We've seen the promise of light, biomancy, and we've touched on the immense engineering effort required for the hybrid PACE-E architecture, especially managing that analog hurdle.
Right.
Now, let's transition to the performance metrics. This is the payoff, right? What does the speed demon actually look like on paper? What are the specs?
Okay, in terms of raw specs, the PACE system operates at a clock frequency of 1 gigahertz. 1 gigahertz.
Okay, pretty standard clock speed.
Yes, but coupled with the optical core, it allows for very high operational speed overall. It achieves a peak throughput of approximately 8.19 teraoperations per second, TOPS.
8 TOPS. How does that compare to, say, a GPU?
It's in the ballpark of some mobile or edge AI chips, but maybe lower than high-end data center GPUs for general tasks. But throughput isn't the main story here.
Right, the latency is the killer app.
Exactly. And its energy efficiency is measured at a respectable 4.21 TOPS per watt. Though it's important to note that figure excludes the external laser power needed to drive the PIC.
Ah, okay, so the laser itself still needs significant power.
Yes, highly efficient lasers are still an ongoing area of research for optical computing. But okay, back to the main event.
Hmm.
Latency. How fast did they get that individual MSC cycle time down?
This is the number I've been waiting for.
They achieved an ultra-low computation latency of 5 nanoseconds minimum, consistently.
5 nanoseconds, 5 billionths of a second for a 64 by 64 matrix multiply and accumulate.
Yes. And the architecture, they calculate, has the theoretical potential to reach 3 nanoseconds, which the researchers' project might be possible in future iterations with improvements.
Okay, 5 nanoseconds. That is the number we really need to hold in our minds because it sets up the drama of the GPU showdown. This is where it gets really interesting because the paper didn't just calculate theoretical speed. They directly benchmark pace against a real-world, high-end commercial GPU, an NVIDIA A10.
Right. A widely used GPU in data centers for AI inference and other tasks.
And they compared them on a relevant real-world task, not just a raw MC.
Correct. The comparison focused on running specific algorithms, heuristic solvers, for computationally hard optimization problems. Specifically, they targeted Ising problems.
Ising problems. Okay, remind me what those are useful for.
They're fundamental models in statistical mechanics, but they pop up everywhere. They're essential in fields ranging from material science, finding stable states of magnets, to logistical optimization, network analysis, even some forms of machine learning. They represent a class of really tough problems.
Got it. So let's look at the single cycle latency difference first. PACE-E versus the A10 GPU for one step of this Ising solver, because you said that number was astonishing.
It is. The A10 GPU's measured latency for a single cycle, performing the same specialized optimization workload, was measured at over 2,300 nanoseconds.
2,300 nanoseconds, so 2.3 microseconds.
Exactly. Now, contrast that with PACE's 5 nanosecond latency for the same single cycle.
5 nanoseconds versus 2,300 nanoseconds. Okay, quick math.
That's a single cycle acceleration factor of nearly 500 times faster.
Wow. 500x. I need to process that difference for a second. For the electronic GPU chip, the data had to move around, maybe queue up, get processed digitally, results moved back, taking over 2 microseconds. The light chip, PACE, basically it did the core calculation almost instantaneously via superposition and was ready for the next iteration in just 5 nanoseconds.
That's the fundamental power of solving the calculation via light propagation, rather than sequential data transfer in digital logic.
Okay, but single cycle speed is one thing. What about the whole task? These optimization algorithms, they need many iterations, right? Thousands of cycles to actually find the solution to converge.
Exactly, and this is where that low latency really compounds its advantage. Latency accumulates rapidly over thousands of iterations.
So what was the total time comparison for the full convergence task, getting the actual answer to the Ising problem?
Okay, get ready for this. The PACE system completed the entire workload, converging to the solution in a total time of just 2.7 microseconds.
2.7 microseconds.
Yeah.
Okay, and the GPU?
The NVIDIA A10 GPU, running the identical optimization task, required 798.1 microseconds to complete it.
Whoa! Okay, 2.7 versus almost 800 microseconds. That's roughly a 300 times speed up for the entire computation.
It represents a 2 orders of magnitude acceleration in total computing time.
2 orders of magnitude. That isn't just an incremental improvement. That feels like a paradigm shift in speed for solving these specific kinds of hard problems.
It really is. When you can reduce a critical calculation from nearly a millisecond down to just a few microseconds, you fundamentally change the classification of what's possible to do in real time.
Okay, so why did they pick Ising problems specifically for this demonstration? Why not something else?
Well, Ising problems are kind of the quintessential NP-complete optimization challenges.
NP-complete, meaning really, really hard to solve perfectly as they get bigger.
Exactly. Finding the absolute best solution becomes exponentially difficult for classical computers. They often become computationally intractable beyond a certain size. They selected this problem set because the heuristic solvers, the type of algorithms used here that find very good, if not always provably perfect, solutions, rely heavily on rapid iterative matrix MAC computation.
Lots and lots of cycles.
Tons of cycles.
Yeah.
The faster the iteration, the quicker the search space of possible solutions can be explored, and the faster the system converges to a good answer. For these algorithms, low latency is the single most critical factor for success. PACE is built for low latency.
It's a perfect match between the hardware strength and the algorithm's need.
Precisely.
And they demonstrated this capability with two specific applications in the paper, right? First, a kind of classic abstract problem.
Yeah, they demonstrated solving a graph max cut problem. This is a common optimization task. Imagine you have a network, a graph of nodes and edges. You want to partition the nodes into two sets, A and B,
Okay.
and the goal is to maximize the number of edges that cross between those two sets. It has applications in clustering, network design. The demonstration showed the PACE system, starting from a random state, evolving iteratively. Each 5-cell cycle refined the state, moving it toward a stable minimum energy configuration that corresponded to the optimal partition, the max cut solution.
Cool. And the second example was much more visual, right? Something involving an image.
Yes, an image memorization problem, which sounds different, but mathematically it can be mapped onto and is equivalent to solving a specific type of Ising model.
Okay.
They took an 8 by 8 pixel image, just 64 pixels total, representing a sort of cat-like pattern. They extracted a 64-node graph structure from this image.
Representing the connections between pixels or something.
Essentially, yeah, representing the desired pattern. Then they started the PACE system from a random, noisy, initial state-like, completely scrambled image.
Okay.
The recurrent algorithm running on PACE iteratively performed these ultra-fast OMAX operations. And over just a few microseconds, it converged back to the stored image, the clean, cat-like ground state solution.
Wow. So it found the original pattern out of the noise that quickly.
Yes. And that convergence, achieved in just 2.7 microseconds, really highlights the power of this ultra-low latency for rapid iterative searches, for finding patterns or optimal states incredibly fast.
That speed is just phenomenal. But as we discussed earlier, speed doesn't mean much if the results are inaccurate, especially with analog computing.
True.
The analog nature of light computing often means there's a trade-off in precision compared to the, perfect 32-bit or 64-bit precision we expect from a digital CPU.
Yeah, it's the common perception, yeah.
So how did the analog accuracy of PACE actually hold up under rigorous testing? Did they quantify it?
They did perform extensive calibration and characterization. To measure accuracy in the analog domain, one key metric is the mean dot product error.
Okay.
The system achieved a mean error of just 0.06 least significant bits, or LSB,
0.06 LSB.
and a standard deviation of 1.18 LSB across all the parallel channels.
Okay, let's pause on LSB. For a listener who doesn't deal with signal processing every day, what does LSB actually measure in practical terms? What does a low LSB error mean?
LSB, least significant bit, is effectively the measure of the smallest change in value that the system can reliably distinguish or represent.
The smallest step size, kind of.
Kind of, yeah. So a low LSB error, like 0.06 on average, means the system's analog output, while continuous, is very tightly centered around the mathematically correct digital result it's trying to approximate. The average deviation is very small.
Okay, so it's quite accurate on average.
Yeah.
And how do we translate that analog precision into a digital equivalent number that maybe we can understand more easily?
Right. The common benchmark for that is the effective number of bits, or ENOB.
ENOB?
ENO. It tells you roughly how many bits of digital precision the analog system is equivalent to. Their results show that the ENOB distribution reached 8 bits of accuracy for more than 65% probability of the calculations.
8 bits for most calculations.
Yes, with an average ENOB of 7.61 bits across all the parallel channels.
Okay, 7.6, let's say roughly 8 bits of effective precision. That's extremely impressive for a large-scale integrated analog system with 16,000 components.
It really is. Maintaining that level of analog fidelity at scale is a major achievement.
Now, hold on. A general-purpose electronic CPU gives you, what, 32 or usually 64 bits of precision for floating-point math?
Correct. Much higher precision.
So why is only 7 or 8 bits of accuracy sufficient for these specific optimization problems, these Ising solvers? This seems like a really critical trade-off the listener needs to grasp. Why don't they need 64 bits?
That's a crucial distinction. You're right. General-purpose computing often does require that high precision for things like financial accounting, down to last cent, detailed physics simulations, or complex graphics rendering. You need accuracy there.
Sure.
However, these heuristic recurrent algorithms, like the ones used for solving Ising problems, are often designed specifically to be noise-tolerant and iterative.
Okay.
They don't necessarily need perfect initial precision in each step. Why? Because the system is constantly self-correcting and converging over many, many cycles.
Ah, so a small inaccuracy in one 5-nanosecond step might get corrected or just overridden in the next step anyway.
Exactly. The algorithm is designed to find the overall trend, the path towards the optimal solution, even if individual steps have some analog noise or slight imprecision. For these kinds of search and optimization tasks, 7 to 8 bits provides enough resolution, enough signal to guide the search effectively towards the right answer over time.
That structural reality of the algorithm allows them to harness the incredible speed of the analog system without being completely crippled by its inherent precision limit.
Precisely. It's a synergistic match.
What's really fascinating here, though, you mentioned the algorithm they used for the Ising solver actually required the opposite of perfect precision in a way. It needed noise.
Yes, controlled noise injection.
Why does a computing machine need controlled imperfections? That sounds counterintuitive.
It does, doesn't it? But this is a classic characteristic of many heuristic search algorithms, especially those trying to find a global minimum, the absolute best solution in a complex landscape.
Okay.
Imagine you're rolling a marble across a bumpy surface with lots of dips and valleys.
Right.
If the surface is perfectly smooth within each valley, the marble is very likely to just get stuck in the nearest valley it rolls into. It's a local minimum. It might be a decent solution, but not the deepest valley, not the global minimum.
Gotcha. It settles too easily.
Exactly.
Right.
And the noise acts like, well, like giving the table a little shake or vibration.
Ah, to shake the marble free from that local trap.
Precisely. The iterative matrix MEC computation needs this controlled noise injection to achieve efficient bit flips, essentially random changes or perturbations in the state vector being computed.
Oh, okay.
This stochastic or random-like behavior allows the system to occasionally jump out of those local minima and continue searching the broader landscape for the potentially better global ground state solution. Without any noise, the system often just gets stuck. It stagnates very quickly.
Interesting. So where did they source this necessary noise? Did they have to add a noise generator?
It actually comes from several places, some inherent to the system and some deliberately injected and tuned. Inherent sources include the laser's own unavoidable phase and amplitude fluctuations, a little bit of noise from the analog driver electronics, and importantly, the thermal noise from the transimpedance amplifier, the TIA, that reads the optical signal.
So some noise is just there naturally in the hardware.
Yes, but they also found they had to actively tune the overall signal-to-noise ratio. They could do this by adjusting parameters like the input laser power or the receiver gain settings. And sometimes they also digitally injected a controlled amount of noise into the EIC's control circuits.
So they're carefully balancing inherent noise with injected noise to get just the right amount of shake for the algorithm.
Exactly. They need enough noise to escape local minima, but not so much noise that it just bounces around randomly and never converges at all. It's a delicate balance required for robust convergence.
And critically, they verified that the high-speed OMAS operation itself was essential, right? It wasn't just the noise randomly finding the answer somehow.
Oh, absolutely crucial test. They ran a control experiment where they basically turned the laser off so the PIC wasn't doing any optical calculation.
Okay.
When the system was only running on its electronic components, the EIC trying to manage the noise sources like the TIA, the output just became dominated by that TIA noise and electronic bias. The channels quickly got stuck on fixed zeros and ones, completely uncorrelated with the problem.
Total failure.
Total failure to converge. This absolutely confirmed that the 5-nanosecond high-speed optical MDAC operation is the necessary engine driving the search. The noise is merely the catalyst, the lubricant, that optimizes the search process run by that engine.
Okay, this is clearly an incredible feat of engineering, this PACE chip. But, no deep dive is complete without a really critical assessment of the limitations.
Absolutely. Need to be realistic.
And this raises an important question for me. If the optical latency scales linearly and is only limited by the physical path length, like you said, why couldn't they push the speed even further? Why are they apparently stuck at a 5-nanosecond minimum cycle time when the theory for just the light path might suggest 2 nanoseconds or even less should be possible? What's the bottleneck?
Yeah, that's a great question. And they actually tested that exact boundary in the paper.
Oh, they did.
They did.
Yeah.
While they achieved that phenomenal convergence rate of over 92% success at the 5-ounce latency.
Right, very reliable.
When they tried to push the system faster, clocking it at a 2 nans latency per cycle, the convergence rate just dropped off a cliff, dramatically, down to less than 25%.
Wow, less than a quarter of the time they could reliably find the solution at 2 nanoseconds. So what failed? Why did it break down?
The limitation isn't the light propagation on the PIC itself. That is incredibly fast.
Okay.
The limitation is the intrinsic delay introduced by the surrounding electronic signal processing cycles on the EIC.
Ah, the support electronics again.
Exactly. The time required for things like the analog to digital converters, ADCs, to read the output, the digital comparators to make decisions, the control logic to prepare the next input, and just the overall clock speed limitations of the EIC chip itself. All those electronic steps still impose an intrinsic delay loop.
So the light does its job in maybe a picosecond or two, but the whole loop, including the electronics, takes 5 nanoseconds minimum to complete reliably.
That's the situation in this current generation of the hybrid design.
Mhm.
It's ultimately capped by the speed of those necessary electronic conversion and control steps. That's what limits the viable operational speed to 5 n's for robust convergence on this particular hardware.
Okay, that makes perfect sense. The whole system is only as fast as its slowest component or slowest part of the loop. And right now, that seems to be the electronic interface.
Precise.
And that ties directly into the larger potential analog vulnerabilities we touched on earlier. If this system relies so heavily on perfectly tuned interference patterns from those 16,000 components, how robust is it really to the messy real world, especially things like temperature changes?
Yeah, the research revealed a specific and, frankly, somewhat concerning thermal vulnerability.
Oh.
The paper states the system is only tolerant to a tenuous 5 degrees C temperature fluctuation before experiencing a noticeable downgrade of an effective bit inaccuracy.
Only plus or minus 5 degrees Celsius?
Yeah.
That's barely the difference between a warm room and a slightly cool room. That seems quite sensitive.
It is quite sensitive. Why? Because in silicon photonics, temperature fluctuation directly alters the refractive index of the silicon waveguides.
The refractive index, how light bends and travels through material.
Exactly. It determines how quickly light travels and, critically for interference, how its phase changes as it propagates.
Phase is everything for interference.
It is. Since the MREA operation relies entirely on those precise phase relationships and interference patterns between thousands of paths, even small, uniform changes in temperature across the chip can throw the entire calculation out of alignment. The interference pattern shifts, and the result becomes less accurate.
So maintaining a very stable temperature across the entire chip is critical for maintaining that 8-bit accuracy.
It seems to be yes. Now, active feedback control systems like on-chip heaters or coolers can be used to stabilize temperature.
But that adds complexity, power consumption, size,
Yeah.
kind of counteracting some of the inherent efficiency gains you were hoping for from photonics in the first place.
Exactly. It's a very real operational constraint that needs to be managed or overcome in future designs, especially for deployment outside controlled lab environments.
Definitely a challenge. Okay, and finally, we really need to address the elephant in the room, workload specificity. We're celebrating this incredible 300x to 500x speed up, which is amazing, but it was demonstrated on a highly tailored problem set, these heuristic recurrent algorithms solving Ising problems.
Is absolutely essential context. Yes.
This architecture, PACE-E as it stands today, it's an outstanding accelerator for a specific, albeit important, niche of computationally hard optimization problems.
Right. That's the correct way to frame it. It is not currently a general-purpose computing solution capable of just replacing a standard CPU or a generalized AI inference GPU for all tasks. Not yet, anyway.
Okay.
The results are heavily weighted by the nature of the iterative optimization problem they tested. That kind of problem perfectly exploits the ultra-low latency advantage PACE offers.
Because it needs tons of cycles, really fast.
Exactly. But if you threw a different complex task at this chip, say one requiring high-precision 64-bit floating point math for a scientific simulation,
The 8-bit analog accuracy wouldn't be enough.
it wouldn't be sufficient. We'd be forced back to slower but more precise digital systems for that kind of task. So the speedup is absolutely real,
Okay.
but it is currently specific to these optimization tasks where rapid iteration and convergence are more important than achieving very high numerical precision in each step.
So while the core 64 by 64 matrix MMAT operation is pretty universal in AI,
Yes.
the utility of the analog output from this specific photonic implementation is currently confined to a smaller, albeit vital, set of problems that can tolerate or even benefit from that lower precision and noise.
Precisely. To scale this approach up to large-scale general AI tasks, like training massive foundation models, they would likely need either fundamentally higher precision photonic components, say achieving 10 or 12 effective bits reliably.
Which sounds like a big engineering challenge.
It is. Or, alternatively, researchers would need to develop new, highly optimized AI algorithms specifically designed to be noise-tolerant and capable of working effectively within the 788-bit analog constraints offered by current photonic hardware.
Okay, so acknowledging those realistic limitations, the two ends electronic wall, the thermal sensitivity, the workload focus, this still represents a colossal step forward for optical computing.
Oh, unquestionably.
So, what does this all mean? Taking a step back, what does this PACE demonstration signal for the future roadmap of commercial computation? Where do we go from here?
I think this demonstration represents a truly crucial milestone in photonic computing commercialization
Why commercialization specifically?
because it proves that very large-scale integration, the 16,000 components, is achievable using industry-compatible manufacturing processes. That 65-nanometer silicon photonics technology is a standard node.
Right, not some exotic lab process.
Exactly. We've now confirmed a plausible path from a laboratory concept to a potentially mass-producible integrated circuit. That's huge for attracting investment and further development.
Okay, and the key technical focus for the next steps must be on breaking that 5 nanosecond intrinsic delay bottleneck, getting closer to the theoretical optical speed limit.
Yes, absolutely. The researchers themselves suggest in the paper that future devices could reliably achieve 3n's latency, maybe even faster, with further signal path optimization and calibration improvements.
Well, how? What needs to get better?
It requires pushing the performance of both the PIC and the EIC components in that hybrid stack. They specifically mentioned things like adopting alternative photonic device designs that inherently have higher bandwidth.
Faster optical switches or modulator.
Eventually, yes. And crucially, tighter circuit designs and faster components on the EIC to reduce those intrinsic electronic signal processing delays we talked about. Faster photodetectors, faster TIAs, faster ADCs, maybe more parallel processing on the EIC side.
Shaving nanoseconds off that electronic loop.
That's the goal.
Ultimately, though, the broader impact here feels almost philosophical as much as technical. It feels like we're not just making existing electronic computations slightly better, we're potentially creating a new computing paradigm where previously intractable optimization problems are now solvable in something close to real time.
I think that's absolutely right. The PACE system demonstration significantly benefits the exploration of completely new computing models and system architectures.
How so?
It confirms that the unique advantages of light, that massive parallelism from interference and the ultra-low latency from propagation speed, can actually be translated into integrated hardware at a meaningful scale.
It's not just theory anymore.
It's not just theory. And this opens the door for developing other dedicated optical or hybrid hardware designed specifically to accelerate other compute-intensive tasks that might benefit from light's properties. Things like sparse matrix operations, which are common in AI, or maybe specialized tensor decompositions.
So the next generation of really high-performance systems might not just be better versions of today's GPUs. They might be fundamentally different hybrid architectures built specifically to exploit light's advantages for certain tasks where electrons fundamentally fall short.
I think that's very likely. It's about leveraging the best properties of both worlds. Light for the instantaneous parallel calculation where latency is king. Electrons for the control, the memory, the precision where needed. That synergistic partnership seems to be where the future speed lies. Hashtag and outro.
Okay, so to quickly recap this deep dive, we've looked at the Photonic Arithmetic Computing Engine, PACE and FEAT, an amazing chip integrating over 16,000 photonic components into a single hybrid system with controlling electronics.
A major engineering feat.
Absolutely. It achieves an ultra-low computation time of just 2.7 microseconds for solving complex optimization problems, like Ising models.
Which represents that incredible 2 orders of magnitude acceleration, around 300 times faster in total time, compared to a high-performance commercial GPU running the same task.
And this speed is fundamentally unlocked by shifting the core computational work, the MA operation, from sequential, data-moving, power-hungry electrons to massively parallel low-loss photons using interference.
With the key being that the latency scales linearly with problem size using light, not substantially like with electronics. And the ability to actually scale these analog photonic components and maintain reasonable accuracy around 8 effective bits at this density is the true engineering breakthrough demonstrated here.
Indeed. Which brings us to our final thought for you, the listener. Think about this. The move from electrons to photons, if it continues to develop, doesn't just make existing algorithms faster. It fundamentally changes which mathematically hard problems we can even realistically tackle in real time.
Right. Problems that were just too slow before it become feasible.
Consider the practical difference between waiting, say, 800 microseconds versus just 3 microseconds for a critical optimization calculation to complete. What new critical applications suddenly become possible?
Yeah, what opens up?
Maybe real-time traffic flow control across an entire city grid. Microsecond-level decision-making for autonomous vehicles or drones reacting to complex environments. High-frequency financial modeling that requires incredibly complex logistical optimization faster than the market moves.
All areas where solving hard optimization problems right now is the key constraint.
Exactly. When previously impossible optimization problems can potentially be solved in a flash, what does that enable? That feels like the real consequence of achieving ultra-low latency with light. It changes the speed of decision-making itself.
A fascinating direction for the future of computing.
Absolutely. Thanks for diving in with us today on the deep dive.
We'll catch you next time.